Hi, I'm Devansha, and this is a video demonstration for data structures and algorithm assignment 2. This is the first question in the class exercises. I have example 1, which starts with constant primitive operations, and then there's a for loop which runs for n times in the worst case. So it has n times constant primitive operations. The line below that also runs for n times constant operations, and the return is only one primitive operation, so it is constant operation. So when we drop the coefficient for the highest degree, the lowest degree variable, and the constant, we can say that big O for this function is big O of n. In example 2, again we start with a constant primitive operations. Then here we can see that the increments are of size u, so we can say that this runs for n by 2 operations, so constant into n by 2 operations. This runs for the same, but as you can see, 1 by 2 is again a coefficient of the highest degree, and we can drop it, and there's no other lower degree variable, so we can say that big O of this function is big O of n. In the third example, again we start with the constant operations. This run loops for 0 to n minus 1, but so it has constant into n time operations. There's a for loop below that which runs for the amount j, so we can say that it runs for 1 plus 2 plus 3 up to n times. So in that case we say that it runs for constant times n into n plus 1 divided by 2 operations in the worst case scenario there is. Again, this runs for the same operations, constant into n times n plus 1 divided by 2. So while we drop all the coefficients of highest degree and we drop the lower degree variables with constants, we can say that the big O of this function is O n raised by 2. In the example 4, there is constant operations, then constant operations into n. Again, these are the same, so when we add, there is 3 times constant operations for whatever this has, and into n operations, but we drop the coefficients and the lower degree variables with constants, so we get again big O of this function is big O of n. This is the last example. uh, we are assuming that the lengths of array are equal, and then we have um, constant operations, constant into n times operations, and this, there's a bracket open here which ends here, so this case runs for constant into n time operations. This runs for n times for itself and n times for the for loop that's above that, so it runs for constant into n times operations. There's a for loop below this line that runs for whatever the value of j is. So the, like in the example 3, we can say that it runs for constant into n times n plus 1 divided by 2 operations. The line below that would run for the same, and this line also runs for this loop, and in the worst case scenario it runs for another n operations if the uh, conditions are not met. And this again is a return, so it's a constant operation, dropping the coefficients of highest degree and lower variables, Along with the constant, we can say that big O of this function is big O n raised 3, which comes from here. Mm, this is the second question. So there are two functions, prefix array 1 and prefix average 1 and prefix average 2. Each of those takes a double array x, and uh, but we can see that there's only one for loop here, whereas there are double for loop here. So we can say that this runs for big O n raised to, and this runs for big O n. But we have this by the RAM operation. Uh, we'll do experimental analysis for this, which proves this. So I'm running the second one, which only runs with big O of n first. I have declared a variable n2, which is the starting point. That is, this is the first array that will be created. I'm going to run this trial for this experiment for 10 times. So it says when j equals 0, j is less than trials, j plus plus. We make the double, that is the size, double array, that is the size of n2. There's a for loop that makes the array. We start the time, we run the function, we take the ending time, and we get the time that has been elapsed, and we print that out. Then we increase the value of n2 and double A. So the second one does the same. It's basically the same thing. Let's run this program. As you can see, the prefix array takes only 2 milliseconds to run the first one, 2 milliseconds for the second one, and so on. It does not take that much time as there is only one for loop, but as you can see, the second one takes more and more time. We'll wait for it to run a few times and then we can go to the another question. If you want, you can skip this part and go to the third question. So it's just the third question, problem of uniqueness, class uniqueness. There's again two methods outside here, unique 1 and unique 2. As you can see, there's two for loops nested inside each other in this uh, function unique 1, whereas there is only one for loop in unique 2. We are gonna run this program now. You can see 50,000 array takes about this minute. This is gonna run for a few minutes. What I'm doing again here is the same. We are starting with 50,000 array. I make this array here and I run this for 30 times. It runs and prints out the minutes it has taken to do this function, and if the function takes more than 1 minute, it prints out this statement which suggests that this is the amount of array that this can take before it hits 1 minute mark. This is going to take some time, so you can skip it to the time on the screen. This shouldn't happen. Oh, so it ran for about 65,000. Oh, 6,050,000. Uh, it ran for this amount of operations before then it hit the 1 minute mark. So this many operations could be done before it hits the 1 minute mark. For the second uh, for the second function, I start with a lot of array, but and I increment it a lot, but it is so efficient that it runs out of the memory before it even hits close to 1 minute mark. So that's it.